Hello, today we are going to do Paul Hewitt's Conceptual Physics, Chapter 11, on rotational mechanics and torque and angular momentum. So, as we've discussed before, force causes acceleration. Remember, if you kick something, it will move, it accelerates. In the same way that force causes acceleration, torque causes rotation, or we can also call rotation angular acceleration. When the angular momentum, the angular position of something changes. So for an example, some of the ways that you use torque in everyday life is every time you turn a screwdriver, you tighten a wrench, you open a door, all of these things, you turn on the faucet, all of these things, you are using torque to create angular acceleration. So the it's called rotation. Angular acceleration is rotation. So for an example, when you turn that screwdriver, you're twisting that. You're twisting the screw. When you open a door, you are causing that door to accelerate, angular accelerate. If you think of a bird's eye view of that door, it's turning. So all of this is torque. Okay, so what is torque? Torque is perpendicular force. So I'm going to write that by saying F, and I'm doing this little guy in the bottom that tells you it's the perpendicular force times the lever arm. Times the lever arm. Force times the lever arm is torque. You can also draw that in the right place. Force times the lever arm. So, an example of this is the door. Is the video still working? Yeah. Okay, Anna, can you go? So for the door example, when you're opening the door, okay, guys, I know you're all famous. Okay. You have to learn physics.
Okay.
Anna. So for example, the longer that lever arm is, the more torque there is, right? The more lever arm you have here, the more torque you have. The more perpendicular force you have, the more torque you have. Well, you might say, why does it have to be dependent? Can you pause the video for a second? So why, you may say, does the force need to be perpendicular? Well, if you imagine, so this is us looking from the sky, and here's a door. Here's the hinge, okay? This is the top of Joey's head. This is the doorknob, okay? Joey is pushing on the doorknob to cause this to rotate. Right, it's rotating in this direction. The door is rotating in this direction. Well, the force that Joey is pushing on that door, you realize, would you try to push that door open by pushing it right near the hinge? That would be very difficult. But what you usually do, or in the middle, but to get maximum torque, reward for your effort, for the same force that you're putting in, to get maximum torque, you want the lever arm, and in this case, the lever arm is always, what is the definition of lever arm? Lever arm is from the fulcrum, or you can think of it as the hinge, to wherever you're pushing the force. Okay, so this is your force. This is your fulcrum. Sorry, this is your force. This is the lever arm. This is your fulcrum. So here, in the example of the door, we're looking from the heavens down at his head. And there's this little arm sticking out and pushing on this part of the door. This is the fulcrum. That's the hinge that doesn't move. The door rotates along, and so here we have the lever arm. We know that he gets the most bang for his buck, the most torque for his force, if he pushes with the longest lever arm, so right at the edge of the door, not near the middle of the door, not near here to the door. You just know, go try it. Go to a door and try it. Try pushing the same amount of force. You get more torque, you get more rotation, more torque when you put your hand near the inside of the door or near the edge of the door. Another thing we'll see is that you want the force to be perpendicular. If Joey puts a lot of his effort into pushing on the door handle this direction, we know if you go to a door and you start pushing the handle sideways and pushing it open, the only force that's really going to make a difference to give it torque to move that door is the force that's perpendicular to that door. Go and try it. You're not going to be pushing sideways on the door handle. Like, you want to push straight so that force is perpendicular to the lever arm as it moves at the fulcrum.
You actually want them to try it?
Not right now. Okay. So here's another example. Here's a girl trying to move a wrench, okay? Wrench is stuck on a rusty bolt. Okay, she's got her wrench, rusty bolt, and she's desperately trying to move it. So will she get any help by taking a rope straight up and pulling on a really long rope here and seeing if this will help her move that wrench?
Her wrench is gigantic.
Giant wrench, yeah. Sorry. She's pulling, remember, perpendicular force, so perpendicular. Will that rope help her? No, actually it won't, because this is not lever arm. She's pulling. This is not going to help her any different than if she was just holding the wrench here and pulling on it, because this is the lever arm. Her adding more and more rope in this direction isn't going to make a difference. You can try this out. You can go get a rope, tie it to the wrench, and see the difference of the force pulling it and pulling directly on the wrench. It's on a rusty bolt, it's heavy. But what will help her, because here her force is the same, whether she's pulling on a rope or holding it there, her force is the same, perpendicular force, and her lever arm is the same. Now, she might get an advantage. Well, never mind, that's complicated. So the other way that she can get an advantage, the better way, she gets no advantage pulling perpendicular rope, is to get an old pipe, flip it over the end of the wrench, and you will instantly feel the difference when you're doing this. I've seen people move all sorts of things by just taking a wrench and then sticking a big heavy pipe over the end. My husband was able to open, I can't remember what it was. It's something to do with jacking up a car with a jack stand that I feel like wasn't working very well. And I was just like, we're never going to be able to do it. It was a short little screw thing on a jack stand. And my husband just went and got a long pipe, stuck it on the end of one, and it was easy to do it. Because you get a lot more torque with a longer lever arm. You'll remember some of this when we were talking about work and machines and force versus distance. We're talking about the same thing. We're just using like different concepts, different words to describe it. This is here we've got the lever arm and the perpendicular force giving the torque. Okay, so an example of that. So far we've been dealing with torque from the fulcrum, to the end of where the perpendicular force is, lever arm. An example of balancing torques is the seesaw. The seesaw, you've got a fulcrum, you've got two lever arms, you'll see here. So to balance a seesaw, there's two kids of equal weight sitting the same distance from the fulcrum on either side. We know that seesaw will not move. You can balance it perfectly. What happens if one of those kids is older? Okay, bigger kid. And we know the seesaw, it's unbalanced. The torque is going to go this way. The torque this guy can produce is small compared to the torque this guy can produce, because there's more perpendicular force of gravity on this side. So lever arms are the same, but the perpendicular force of gravity on this guy is more. So we know in this case, the seesaw will do this, and the big kid will be on the ground. The little kid will be up there. The little kid is producing torque, but the big kid produces more torque. So is there a way to balance a seesaw with a big kid and a little kid? And if you have ever played on a seesaw, you know that there is. And the way to balance the torques between the little kid and the big kid is you can't change the force as being different. The big kid's going to have more force of gravity on than the little kid. But what you can change is the lever arm. So here's you've got your big kid, and you've got your little kid way at the end here. And you can see the reason they can balance the seesaw is because the lever arm that we're going to measure, where the force is, the perpendicular force on the lever arm here, is where gravity's pulling on these kids. This is a short lever arm times a bigger force, a smaller force times a longer lever arm. They have equal torque. So if it's balanced, look, they have equal torque, the same torque. With the little guy, he's got a little bit of force, gravity on him, but a big lever arm.
Yeah.
See? And on this side, balance the torque, he's got a big perpendicular force, but he's got times a small lever arm. You see how that balance is there? And so that's how they're able to balance it. Or sometimes you'll see, instead of a big kid, you'll see a bunch of little kids. So sometimes you go out to the playground and look at a seesaw, you'll see a bunch of little kids sitting on one side very close to the fulcrum, and you'll see one little kid way out at the other end. And those are kids experimenting with balancing their torques. Okay, so then back to the kids on the seesaw. We saw how he was able to change his lever arm by moving where he was, by scooting closer to the fulcrum.
Yeah.
And that is because if you take an object,
Mom,
you
can I
pick
pause
this,
it?
yeah, go ahead and pause it. So a lot of times where we measure that lever arm is really about the center of gravity. So for example, if you want to kick a football, here's a football. The center of gravity is right there, okay? If you want to kick that football and just have it sail straight through the air, you kick it and you put your force in, here's your foot. You kick your force in line with the center of gravity. And then it won't really get any rotational inertia. Why? It'll just go sailing through the air. Why? Because the lever arm is 0. You'll see what I'm saying in a minute. If you want that football to spin like crazy when you kick it, see center of gravity is right there. He's going to kick it either up here or kick it with his foot or kick it down here. Why? Because the lever arm is as if the fulcrum is the center of gravity and this is the force. The lever arm is the distance between the center of gravity and where the perpendicular force. So if he kicks it like this, it's going to spin. That football is going to go through the air spinning. It'll be rotating. Try it out. Take like a object like this, try kicking it in line with the center of gravity, try kicking it at the end. You can even do this with a round ball. You kick it dead center, like a soccer
Do you
ball.
actually want your
You kick it
physics
here.
students to do all this random stuff?
Yes, you experiment and you realize if you want that thing to spin like crazy, you kick it either low or high. To maximize, here's that lever arm, there's the center of gravity that's like the fulcrum here, and then this is your perpendicular force. Okay. So, rotational inertia. So we've talked about what is torque. Well, instead of writing lever arm, you can also just write a big L. Is this still on the
Yeah.
sweetie? Times L. Okay. So, rotational inertia. So we know what inertia is. Inertia is the kind of the laziness of matter. When stuff doesn't want to stop if it's moving, or if it doesn't start moving if it's stopped moving. So rotational inertia is like that, but it's talking about the inertia that something has that's rotating. You will see the rotational inertia if you spin a top, those little toys, and you spin it. I mean, this thing has rotational inertia too, but not as much as the top. Okay. You take a top and you spin it, and you just watch that thing spin, spin, spin. Rotational, you know, when you start spinning a quarter or a penny and you watch it go, 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 that is rotational inertia. It's starting to spin. It doesn't want to stop spinning. Slowly, you know, its energy's bled off. I made friction with the table, whatever, and it will slowly stop spinning. But rotational inertia is the same as inertia, but it's about, it's rotational. All right, I'm sorry, I have a headache. Okay, so for example, you feel if in a battle, if you're fighting or if you're doing sports or whatever, if you have a longer sword, you can feel it. A longer sword has greater torque, greater rotational inertia, right? And remember, that's what we were talking about balancing. And the center of balance of that sword is here, you know, versus if you make that sword even longer. And now the center of motion is there. So here, your hand is here. So this is like your fulcrum. Your hand is the fulcrum. So you'll say, okay, here the lever arm is there. Here the lever arm is here. There's a huge difference between fighting with a sword whose center of gravity or center of mass is much further out. You will feel it. You'll instantly feel it. This is that's also in baseball. When people are swinging a big bat in baseball, the longer that bat is, like the longer that bat is, the more rotational. It's like the world's ugliest baseball bat. The more rotational inertia that baseball bat has. The longer it is, the harder it is to start getting it to swing, but the harder it is to stop it from swinging. It's got rotational inertia. It wants to just keep on swinging. This is why if people want, a lot of times when baseball players want to have more control over their bat, they will, what people call choke the bat. They will put like one hand here where the fulcrum, instead of two hands being way down here. Like a home run, you don't want to choke the bat. A home run, you want to get as much swing as you can out of that thing. Most rotational inertia. But when you're trying to do something else, choking up on the bat is when they bring one hand up here. All of a sudden, your lever arm, so if you don't choke the bat, you got two hands down here, your lever arm you'll see is all the way here. But if you choke up on the bat, the rotational inertia of the lever arm is shorter. Okay, so this is another reason that battle axes battle axes were never, I mean, they're in a lot of fantasy stories, but they were never really hugely popular in like real warfare. And the reason is because a battle axe has a huge amount of rotational inertia.
What are you calling a battle axe?
I'm talking about an axe used in battle. Or a war. Okay, let me
Any
rephrase
axe?
it. Okay, let me rephrase that. Here's the point. People did use battle axes. I'm talking like the big, heavy, fantasy-looking battle axes.
Giant
People's
heads.
with giant axe heads. So, okay, I'll rephrase that. Warhammers. Warhammers were not very commonly used.
Warhammers
because,
are not axes.
Okay, good point. The more mass you've got at the end of that thing, the more rotational inertia it has. I mean, just pick something up and play with it. You will feel it. The more that mass is over there at the end, and you're swinging it, like the more like gravity, that force is there. You've got your little fulcrum here. The more rotational inertia it has. Because long lever.
durable.
What? I don't know. I'm guessing axes would be more durable than swords. But this isn't about that. Let's finish, okay? So the more swing, the more torque it has. Isaiah, let me finish the physics. Okay, I gotta finish this first. So another example of this is try running straight-legged, and you will feel the rotational inertia of your legs. When you run, one of the reasons you bend your knees is to decrease your rotational inertia. You're decreasing that lever arm. You're decreasing the rotational inertia of your legs, so it's easier to whip them through the air. If you try running straight-legged, you will feel that extra rotational inertia of your legs with this longer lever arm. See, if you're running, here's your fulcrum, I guess, is your hip joints. If you run long-legged, see, that's the lever arm there, more rotational inertia. If you bend your legs, if you're bending your legs, the effective lever arm is much shorter. And so it's a lot easier to run bending your knees than it is to let them try to run straight legged. Okay. Another example is a rotational inertia. It doesn't want to resist rotation. Is the reason that tightrope walkers will walk back when people had surfaces will walk with those really long poles. Is that long pole has rotational inertia? It resists rotating, which is tipping off of the rope. A more relevant example is if you bike. And you will know that trying to balance on a moving bike without tipping over is so much easier than trying to balance on a bike that's just standing still. And the reason is because as you're biking, those wheels that are rotating have rotational inertia. And the bike, if you watch someone biking really fast, they can sort of tip from side to side and they're not tipping over. I mean, they can sort of lean and they're going. Because those wheels that have rotational inertia, they're spinning and they resist tipping over. They resist rotation, which in this case is you tipping over and hitting the pavement. Okay, so each object has its own rotational inertia. That is basically a equation. Each object, so if we're talking about a ball, donut, human, I mean, everyone has their own, human in specific, every position you put when you change, redistributing how your mass is, and how you're distributing it, that changes your rotational inertia. So rotational inertia is they often call it I for an object. So the rotational inertia of a sphere. Can you please not play that, sweetie? It makes me laugh. The rotational inertia of a solid sphere is 2/3 its mass of the sphere times the radius of the sphere squared. The rotational inertia of a cylinder, you'll see these depend on the mass and the size. The rotational inertia of a cylinder will be 1/2 times the mass of that cylinder times the radius of it squared. A solid cylinder actually has less rotational inertia than a hollow cylinder, even if their masses are the same. And this is why, if you ever get, it's why our bicycles are hollow in the middle, or why our bike wheels are hollow in the middle. If you were riding with a bike with like solid rubber wheels, you would not have as much rotational inertia. It would not resist tipping over and whatnot. You will see this, even if the mass of those wheels is the same, if you get if you have the same, you weigh them, you use the exact same amount of rubber, one of them is like a solid wheel and the other is like the regular, the regular bike wheel with the inside is just spokes, you will see the difference. Ice skating and gymnastics is all about changing your rotational inertia. So a human being whose rotational inertia, when their arms are spread out like this, has more rotational inertia than a human being whose arms are tucked in. So you will see this a lot. People changing in ice skating, you'll see people changing their rotational inertia a lot. They'll be spinning around with their arms out, and then they'll draw their arms in, and all of a sudden they're spinning really, really fast. You can see this also when kids are doing acrobatics on like those hanging loops, and they're spinning with their arms out like this, and then they pull their arms in, and then that loop just starts spinning faster and faster, and then they put it out, and then it slows down again. Ice skating and gymnastics are all about changing your rotational inertia by changing like the distribution of your mass, because your eye, the rotational inertia here depends on the distribution of if your legs are, if you have one leg out, do you have both legs together? Like how are you holding yourself? Where are your arms? And also what axis are you rotating around? So to give an example of that, before I give an example of that, what is the conservation? Remember the conservation of momentum, MV, right? Conservation of momentum. So that means that if the mass changes, or the velocity of the mass, if the mass is bigger here, we have a smaller V here, and here if we have a smaller M, and we have a bigger V. And we saw this with like a little marble hitting a big ball, or a big ball hitting a little marble, and the conservation of momentum. Now, rotational inertia, or I should say angular conservation of angular momentum, which is like the twisty version of this, is I omega, that is conserved. So let's say the ice skater has it puts her arms out, okay, and one leg out, she's balancing one foot. She has a really big I, okay, so her omega, the omega is the angular rotation, so how many rotations per minute, okay? So her omega, say, is smaller, so she's only rotating once per minute, and she's got that big I holding her arms out like this. Then she's suddenly going to pull everything in, okay, around her axis of rotation. Remember, her axis of rotation is right, like, down her body, okay? That's where she's rotating around, this ice skater. Now she pulls her arms in, her legs in, she's going to be spinning much, much faster. So what did she do here? She made her eye smaller.
Oh,
now her omega would be bigger.
In aerial arts here on the hoop thing, she go like this. It's gonna go really fast.
So Kazia here is doing aerial arts where they have a hoop, a dangling hoop, and they sit inside of this hoop, and they find that she said if you put your legs out or your arm out, you are spinning slower, because here they have a very big eye when they do that, and they're spinning slower, like only say once per minute. And then they pull in their arms, they pull into that hoop, and what do? They just made their eye smaller, their rotational inertia is less, and so now all of a sudden their omega, their angular speed, rotations per minute, goes much, much faster. So now they're spinning, 10 times per minute. So you'll see them put their arms out, spinning slowly, pull it in, and all of a sudden they're spinning really, really fast. So what they're doing is they're changing their eye by changing how their mass is distributed, where their center of gravity is, or what axis they're rotating along. So when I say what axis they're rotating along, you see that more in gymnastics. So in gymnastics, you will see often there's like a high bar, and you will see like a gymnast, holding on to their arms like here, their heads here, their legs are out here, and they're flipping around and around that bar. Kind of slow, you see them doing it sort of slowly, say whoa, whoa, like that. And then they will often let go and then bundle themselves up into a little ball, like a little somersault. And they will be spinning much, much faster. And then they will suddenly spread out their arms and legs and land gracefully with their arms in the air. So what are they doing here? When they go swinging round and round, and then they pull off the ball, they hold their arms and legs together, they go spin, 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 and then they suddenly stretch themselves out and land. What they're doing here, by their axis of rotation is way over here. Like their whole body is to rotate around this pole that is around the bar that is their axis of rotation. So they have a very long, lever arm here. They have a big eye, okay? Big eye and a medium omega. So what do they do here when they're flying through the air and they tuck their arms and legs in and they're spinning, spinning, spinning? Here what happens is they have made their eye smaller and their omega is bigger. And then at the last minute, they stretch their body out again. So their axis of rotation is probably their middle now. Because here the axis of rotation was the middle. Here the axis of rotation was here. But since they stretch their body out, the eye gets bigger again. And so then the omega slows down. And then that's where they sort of land gracefully at the end. Though here they probably have the smallest and the biggest eye because their axis of rotation is way over here. Here the axis of rotation is in the middle of their body. So the eye here is going to be the biggest eye here, smallest eye here, and then medium eye here when they land right at the end. And you will see that reflected in the omegas. And you'll see in their angular speed, you'll see here it's like 1 rotation per minute. Here they're doing, 20 rotations per minute. And then here at the end, maybe it's like 5 rotations per minute. I don't know. You can probably time it, play it in slow motion, and you can see this if you're ever watching like Olympics, gymnastics doing the things on the bar where they do those flips. Now you can test this out yourself. If you're an ice skater or something, that would make it really easy. But another thing you can do is take 2 weights. And I was trying to demonstrate this, but I set off like vertigo, so I'm not going to do it again. So all you young and healthy kiddos, get 2 weights. Wait, we're almost done. Get 2 weights and hold them in your hands and start spinning around. Make your eye really big. So make lots of rotational inertia. Put your hands way out and spin, spin, spin with those weights. And then as you're spinning, wear like slippery socks so it's easy for you to spin on the kitchen floor. Pull your arms in and you will feel yourself spin like crazy. I wish I could demonstrate it, but I got really dizzy when I did it. It works. Try. Okay, so this is you proving the conservation of angular momentum because big I, conservation of angular momentum. You've got big I, small omega, but then if you change your I, the angular momentum is conserved here, and then big omega. That's your, remember this is your speed, this is your rotational, your moment of inertia is what they like to call it. Like the kind of the intrinsic rotational inertia that you have for a given object. Okay, the best advice I can give is go and watch a whole bunch of YouTube videos on, just look up ice skating, conservation of angular momentum, and you will find all sorts of beautiful demonstrations. You can even see conservation of angular momentum experiments people did in space. It's really fun because you can just see them floating in the air and doing various things. But to get a really intuitive grasp of rotational mechanics, you really have to watch a lot of gymnastics, watch a lot of ice skating, and you'll see it. All of that sports is rotational inertia. Thanks. Yeah, don't worry about that. All right, thank you. Sorry, that was such a chaotic lecture. Thank you.